Hello, everyone. So you saw my email. Since the school year is now over, at least for me, Zoom is no longer allowing me to do like large meetings for that are over 40 minutes in length. So my best guess is that Zoom is going to kick us out 40 minutes into the class, and then all of you are going to have to come back in. But this afternoon, I actually I tested it out on 4 devices. I tested it out, and then it actually didn't kick me out. So let's see what happens. So so if it does, please enter the same code and join the meeting then. All right. So are there any questions on the homework? Were there any problems you had? And did any of you find out which question had the wrong answer?
No.
So I think Travis did find it. So if you didn't find it, it was number 9. And I think if you were to look over the answer key, you would have been able to see that number 9 was completely unrealistic. So yeah. So someone's asked me to go over number 7. So let me get out my whiteboard here. So if you would all pull up number 7. So number 7 says a 15 kilogram box is moving to the right at 25 meters a second and is being pushed towards the left at a force of 10 newtons by an external and non-frictional force. If the coefficient of kinetic friction is 0.3, how far will the box go before it stops? So we have a box, all right, and it's 15 kilograms. And it's going to the right at 25. And it's being pushed to the left at 40 newtons by some kind of pushing force that's going on by an external non-frictional force. All right, and then it's telling us about the coefficient of kinetic friction, which basically reminds us that there's also kinetic friction trying to oppose this box's motion. And remember that the formula for kinetic friction, that force, is the normal force times the mu k. All right. So what is the normal force in this situation? Well, there's mg pulling it down, and since it's not going up or down, my normal force is the exact same thing. All right. So you could have gone through the equation thing, but most of the time you can use your common sense. So in this case, normal force is mg. So my opposing kinetic friction force is mg mu. And what is that? That is 15 times 9.8 times 0.3, 44.1. All right, so now we have 2 forces trying to oppose this box's motion. So in total, we have 40 plus 44.1 equals 84.1 newtons of force, right? So from this, we can use F equals ma to find this box's acceleration. So 84.1 divided by 15 is equal to the acceleration, A is 5.6 meters a second. All right, so we have this acceleration opposing the 25 meters a second forward. And so if we use the formula A equals change in V over T, our 5.6 is going to equal to, oh, it's asking for how far it will go. So instead of using this formula, we're going to use the formula where it is V squared equals V0 squared plus 2AD. All right, so it's basically going to be 0 squared, because that's our final speed, equals 25 squared plus 2 times negative 5.6, because it's in the opposite direction, times my distance. And it's just solving that. We get 55, or it's 8 meters. Right, I think that's the answer, unless I did something wrong there. All right. Sean has raised his hand. Is there a problem?
No.
Okay, that's good. So now I'm going to get on with the meeting and the class. So if you weren't here at the beginning, well, so the thing is, if you saw my email, Zoom won't let me go for a class over 40 minutes now. All right, so I'm going to expect Zoom to kick us out at maybe at 8:37 or something, because that's when I started class. So when it kicks us out, please log in again with the same exact code, and you should be back into the class. All right. So hopefully we'll be able to work through that obstacle. So let me get going with class now. We have week 4 physics, and we're going to go on with our Newton's laws. So part 2 of Newton's laws. And this week we're going to go over common applications of Newton's laws. All right. So this is going to be a very real world type lesson. And we're going to go over like a ton of real world things. So hopefully this will be rather interesting. So first of all, we're going to go through the key points from last class, because these are going to carry on into this class. And then we're going to talk about ropes and tension force, pulleys, inclined planes, blocks. Well, that's pretty vague. I'll go over that later. And then stacked blocks. All right. So I'm going to review the key points right here. So remember, the first key point is the sum of all forces equals mass times acceleration. All right. And what does the sum of all forces mean? This is the sum of all the vectors. So if I have some kind of box and I have a ton of forces pulling it, we add all these vectors together. All right. So let me first. Okay. So we add all these vectors together, and that will equal to our sum of the forces. Right. So that is the second law. And then we have the third law. I'm not going to write it out here, but please, please, please remember the third law. All right. So whenever we have forces working, you always have to remember the third law. Very, very important. And then we have normal force as the force a surface exerts on an object. All right. And this is perpendicular to surface. All right. So when we go over inclined planes later, the normal force is going to be perpendicular to the surface. Okay, it's not going to go straight up. All right. And then the last key point is that friction is the normal force times whatever coefficient of friction that is. All right. So let's get on with ropes and tension force. All right. So let's first imagine a game of tug of war where we have two people pulling on a rope. Okay, so we have this rope here. Right. So when we pull on the rope, we're gonna, by common sense, the rope is gonna try to force us back, right? So this is the force within a rope, and this is what we call tension. Tension is just basically the force a rope can do. Can apply. All right? And tension is uniform, at least in this class. We're going to consider it as uniform throughout the rope. All right? So if we have some kind of tension on one end of the rope, we're going to have the same exact tension force on the other end of the rope. All right? So in this case, our tension forces are pulling the people together. Because obviously this person's trying to pull himself backwards. This person's trying to pull himself backwards. And there needs to be an opposing force to this force, right? Otherwise, this person's just going to fall backwards and hit his head on the ground, right? So in this case, tension force is going towards the middle of the rope. But it's not always towards the middle. Another common problem we can have is a tightrope walker. Right, we can think of a man standing here, right? A tightrope walker stands on a rope, right? So the tension force inside the rope needs to support this tightrope walker in this case. If the tension goes down like this, obviously it's just going to push this guy down. It's going to make him fall, right? We have some mg here, and the tension forces will need to oppose gravity. So in this case, tension is actually going upwards, right? Because if we were to now turn this tension into an x and y component, we can see how there are upwards forces acting within the rope, which will support this man on its tightrope. All right, so the tension in a rope actually depends on the situation. All right, are there any questions about tension? Okay, so here are two problems for y'all to do. So Fiona raised her hand. You have a problem, a question?
Yes, so tension force is applicable to ropes, but
Yes.
like exactly what, like more generally, like leaving the world of what you expect from a problem, what other like mechanism would be like suspected tension force?
So
Is it
your
only
question, like,
applicable to like ropes, or
tension
just
is only
like,
the
general?
force within a rope. All right. So for example, with this, the first question here, we're gonna have a rope tied around a 10-kilogram box, right? Of course, I'm not pushing on the box myself. The rope is. So the tension force is actually what lifts the box. All right. So this one shouldn't be that hard of a problem. So I'll give you guys maybe 3 minutes. So basically what I did here is this is a force diagram, or basically force analysis. All right, so this is a diagram where I label all the forces, and this really helps clear up stuff when I do problems, because I can't just look at this problem and go like, boom, I know what to do. So I need to draw out a diagram with all the forces acting on the object. So this is really important. I highly recommend doing this when you do physics. Well, I guess it's almost highly critical that you do this when you're doing physics. Okay, so it's always important to draw out these force diagrams, labeling all the forces within the realm of the system. All right, so when you get an answer, please privately chat that to me. Okay, so I'm going to talk through these problems now. So I see someone's giving me an answer. So here, I'm tying a rope around the box and I'm lifting it off the ground, which implies that there is 0 acceleration. And the box is just dangling in the air, all right? So at this point, since the box is not in contact with the ground anymore, there is no normal force. So basically, the ground has to be in contact with the box in order for there to be any normal force, all right? So the only two forces are my tension and my gravity. So my net force is 0. So 0 equals, if I establish a positive and a negative, tension minus mg. So tension equals mg, and that will be 98 newtons. All right. Now for the second problem. A 60-kilogram tightrope walker is walking on the rope, and so we need to find the tension in the rope. So first of all, there's this mg force pulling this guy down, and the tension force will need to act this way. All right, so tension, tension, all right? And tension is uniform throughout a rope. And so if we can't just add these right now, right? Because they're not vectors pointing in the same direction. So we need to take this tension and put it into x and y components. So we can use our F equals ma equation on this mg. So basically, this tension will be in two components. The one going up will be t sine theta. Going to the right is t cosine theta. All right, if you have trouble visualizing this, maybe you could flip this triangle on its end. You have a tension here, 5 degrees. All right, so, and then we have the other tension force pulling up as well, t sine theta, t cosine theta. All right, and since these two t cosine thetas will balance out, we don't really care about them. All right, so what we see here is that these two t sine thetas are going to oppose our gravity. So my net force, since he's not moving, is 0. If we establish a positive and a negative, we have actually two t sine theta components. Minus, because mg will be negative. All right, so 2t sine theta equals mg. So t will equal to mg over 2 sine theta. So if I plug that into my calculator here, 60 times 9.8 divided by 2 divided by the sine of 5, tension will be 3,373 newtons. Alrighty, so that is actually quite a large force, which is why tightrope walkers need really, really thick and strong cords that can keep them up. All right? So now we have pulleys. So I'm sure all of you have learned about pulleys in maybe like first grade or sixth grade, maybe not sixth grade, but something like that. And basically a pulley has a string, a rope around it, and with two weights attached to it, something like that. All right? So a common physics problem with pulleys, let me just give these two boxes some kind of mass. And let's just assume that mass 2 is greater than mass 1. All right? So if we were to look at the forces, so sometimes the problem is going to ask us about, hey, what's the acceleration of these boxes? Like, where is it going to go? Like, how fast is it going to fall? So since we know that mass 2 is greater than mass 1, we know it's going to fall this way, right? So in this problem, if we just assign a positive and a negative like that, that's not going to work, right? Because if we look at this rope, we have a tension force pulling up, right? But if we set the positive direction as up, then we have these tension forces both going in the same direction. But obviously, if we're to stretch this rope out and put it on the ground, these tension forces are not going in the same direction. You see that? You guys see that happening here? Right? So, in this case, we can't actually define a positive and negative straight out of the bat. We have to look at the sideways, the lying flat diagram here and see how we can just define a positive and a negative like this. All right, so in this case, if we have defined a negative like as here and a positive as here, Then we're gonna have a negative up here and a positive down here. Alrighty. So if we look at the forces here, there's an M2G force pulling it down, pulling mass 2 down. And what's pulling it up is the tension in the rope, right? So the net force on mass 2 is M2G minus the tension. All right. And what is the net force on mass 1? Well, we have an M1G pulling it down and a tension force pulling it up. So it's T minus M1G. All right, does everyone see that happening? Okay, so since these two boxes are connected by the same rope, if one box goes up at some rate, the other box has to go at the same exact rate. They're kind of stuck together, right? So this is a really important thing. We can notice how A will be constant for both boxes, because if one box goes up this way, it in some acceleration, the other box has to go in the same exact acceleration. So if we take these two forces and make them into F equals MA, then we can replace the first one with M2 times A. We're going to replace the second one with M1A. All right, so now you have two really handy-dandy formulas you can use to solve for what you want. All right, so in the actual problem, they're going to give you some values, and you're going to plug these in. And this is actually not the most efficient way. I know some of you are wondering. This is actually, we can see how this is kind of tedious. So if we go back to our diagram here, we can label the gravitational forces on this one as well. If we were to stretch it out like this, there's an M1G, and there's an M2G as well, right? Can everyone see that happening here? So since these two masses are connected to each other, we can actually consider them as one big ultra mass of M1 plus M2. All right, and you might ask, wait, what about these tension forces? Don't they matter too? But as you can see here, these tension forces are going against each other. They're gonna equal out. They're gonna cancel each other out. So in the end, these are actually irrelevant to our problem. And these are what we call internal. If we look at a system and we see forces working within it, like such as these tension between the ropes, then we can ignore that if we consider the whole system as one, as I just did, like as right here. All right, so this is actually an easier way to do this, right? Because we have an M1G. Oops, my pen is not working. M1G. And we have another force, M2G. Right, so this is a lot easier diagram to look at because we just have these two forces acting on it. If we establish a positive and a negative here, then the net force is M2G minus M1G. All right, and since F equals MA, this will just equal M1 plus M2 times whatever acceleration. All right, so if the question gives you values for M1 and M2, you can find the acceleration according to this formula. All right, so it's best not to memorize this formula actually, because it's always better to understand how these forces are interacting. All right, does anyone have any questions about that? So the first method with the tensions does work. It gives you the same exact result, but I would always prefer to use this ultra box method, if you will. All right, so some problems. All right, now I'm going to go over these problems. So the first one, I'm going to have a pulley. We have a big 6 kilogram and a small 3 kilogram. So we know the box is going to, these boxes are going to accelerate in that direction. So can everyone hear me fine? Because my internet is not that good. Just wanted to make sure. Can everyone hear me? Good, okay. So okay, if we were to take this system and were to put it horizontally flat, like this, right? You can see how there is some kind of 6G force attracting that way and a 3G force this way. All right, can everyone see that happening there? So now we have the tension going inside the system. All right, and now I'm actually going to look at this whole thing as one box, because since they're stuck together, they're basically just like one box going a big clump of 3 and 6 kilograms. So it's 9 kilograms now. And since the tensions will cancel out, I'll just have a 6G going this way and a 3G going this way. So my net force is going to be 6 minus 3, 3G. So this is my net force. All right, so this would be 29.4, which is a lot of the answers that everyone gave me. But this is not quite the acceleration yet, because F equals ma. So 3G will equal the mass, which is 9. So you got to be careful. The total mass is now 9 times the acceleration. So if we take 3 times 9.8, divide that by 9, we're going to get 3.27 meters a second squared. All right. So now the second question is really like basically the same thing. All right. So we're going to have we have a 5 kilogram, 6 kilogram, and both of these boxes are 10 meters above the ground. All right. So basically we want to find out how long it would take for one of these boxes to hit the ground. Well, obviously it's going to fall this way. And so we're going to try to figure out how long it will take for the 6 kilogram box to travel the 10 meters down to hit the ground, right? So basically this calls for the kinematic equation where it goes d equals v0t plus 1/2 at squared. And since there's no v0 here, all we need to do is find the acceleration of the system and plug that in, and we'll have the amount of time it will take. All right. So basically, this is just like the first one for asking for the acceleration of the system. We just have this extra step here where we need to plug this into a kinematic equation. All right. So if we were to take this whole system and put it out like this again, flat, we're going to have 5G pulling this way and 6G pulling the other direction. Tensions are going to go within each other and they're going to cancel out. So if I consider this as a one ultra mega box with weight 11, mass 11, so we're going to have 6 kilograms, 6G and 5G. The net force is going to be 6 minus 5, just G. So G is the net force. And since F equals ma, G equals the mass times the acceleration. So the acceleration is 9.8 over 11. All right. So since the acceleration is now something like 0.89, we plug this into our equation and solve for t. 10 equals 1/2 0.89 t squared. Right, and if we're to solve this, 10 times 2 divided by 0.89, take the square root, 4.74 seconds. Okay? Are there any questions? Okay. Inclined plane. Alrighty, so this is, for example, all the questions we've been working with so far are on flat surfaces. So now what if we had something inclined, like a ramp, and we had some box on it? Well, obviously we're going to have mg pulling it down, right? And now we need to remember that the normal force is perpendicular to the surface. It's not going directly up now. It's going kind of like on a slant, all right? So if I label a theta here, well, if I look at these forces, I have an mg pulling it straight down, and I have a normal force at an angle. How can I analyze the forces this way, right? I want to have everything in some kind of perpendicular plane with two perpendicular axes, right? So the actual preferred way to do it is actually to shift our reference of view. So it kind of looks like this, where the box is actually kind of flat. Can everyone see this? So this is the ground. I've like shifted my head over, so I'm looking at it at this kind of angle, right? So in this case, our normal force will be directly up. But what are these forces? Well, obviously this box is going to slide down some way. So what are these forces going on in these directions? Well, instead of writing mg like that, if we write mg as a vector, right, we have that as a vector right there. If I were to draw an altitude in this triangle, in this big triangle here, right, now I have an altitude. So now I have these similar triangles here. So now since this is theta, this is 90 minus theta, so this is also theta, all right? So in this case, mg cosine theta is actually going in this direction, all right? Perpendicular to the plane. And what's going this direction? That's mg sine theta. So now if I label these on this graph, this is mg sine theta and mg cosine theta is going down, all right? So in this case, if there's nothing resting on this box, if it's just this box, then my normal force is also going to be mg cosine theta, all right? So if I had some kind of frictional force on this ramp, well, what's that going to be? That's going to be my normal force times some kind of mu. All right, so this is basically everything about the inclined plane. All right, so something important to remember here, mg sine theta goes straight down parallel to the inclined plane. Mg cosine theta is the normal force acting on the object, and mg cosine theta times mu will be the frictional force if there is any. Okay, are there any questions about that? So this is something you should remember at least, or maybe take a screenshot of this because you don't really want to derive it every single time you do it. So let's do some problems with this. Two problems. I'm going to give you maybe like 3 minutes. So by the time you guys might be done with these, I expect Zoom to kick us out. So if that happens, let me chat in the meeting code. 4329. All right, so if that ever happens, put in the meeting code and the password is 1234. All right, so hopefully if Zoom kicks us out, I will immediately start the meeting again. And yeah. So for a refresher here, I have a box right here, and downward force is mg sine theta. Right, so this is the force that's actually pulling it straight down the plane. If there's no other object on the box, mg cosine theta is up. That's the normal force. So frictional force is going to be mg cosine theta. Doesn't seem like Zoom wants to kick us out. So maybe it will. I don't know. So I'll go for one more minute. And these two problems. So the second one is actually a competition problem, a kind of a common competition problem. So don't be afraid if the second one is a little hard. So apparently I don't think Zoom is going to kick us out, which is great news. Maybe it's glitching or something, so I'm just going to continue with class this way. So, all right, so let me go through the first one now. We have a 20 kilogram box on a frictionless plane of 20 degrees. What's its acceleration down the plane? That's going to be this vector right here that's causing the acceleration down the plane, and that is mg sine theta. And since there is no frictional force, there's no other force accelerating this, there's no other force in the parallel direction to the plane. So the net force is mg sine theta. So this equals ma. M's cancel out. A will be g sine theta, which is 9.8 times the sine of 20, 3.3. My pen has stopped working again. Meters a second squared. All right. So now the second one, the coefficient of static friction on an inclined plane is 0.43. What is the minimum angle this incline must have such that a box placed on it will start to slide? All right, so we're going to have some kind of angle theta here and a box. We know that the mu equals 0.43. Right, so if you've experimentally done this before, you know that if you incline some kind of, let's say this is my calculator on my hand, well, it's not falling yet, but at some point it's going to go boom and it's going to fall off, right? So we want to find that point. And what's preventing this thing from falling? There's always going to be an mg sine theta force going down, right? So what's preventing this from falling is actually the static friction force, all right? So we know that static friction has a maximum value. It can't go above this value. And this value is given by normal force times the mu, right? So once the mg sine theta force exceeds static frictional force, then it's going to start to slide. All right. So basically, we just want to find the exact point where mg sine theta is going to equal to our static friction force. Because anything above that, it's going to slide. All right. So mg sine theta will equal to our frictional force. All right. And what is that? Mg sine theta is going to equal to my normal force. What is that? This is mg cosine theta. Mg cosine theta times my mu. Alrighty, the mg's will cancel out. And so it's wanting to find the angle on it. So what do I do here? Well, I can divide both sides by cosine theta. So sine theta over cosine theta is tangent theta. Tangent theta equals mu. If I take negative tan on both sides, then I have theta is the negative tangent of mu. And what is that? Well, let me do that on my calculator. And then the inverse tangent function is the second time, and then clicking on the tangent. So theta will be 23.27 degrees. Alrighty, so once this slope goes over 23.27 degrees, the box is going to slide. All right. Does anyone have any questions there? All right, good. So now, let's skip this one, because I'm getting low on time here. So here I'm going to talk about blocks. It's kind of a vague category if you were to ask me. Well, I didn't really know anything I could describe this as. So sometimes we're going to have two blocks on a table, all right? And we're going to have some kind of force here, and the problem might ask us, oh, what's the force that block 1 exerts on block 2, right? Because there must be some kind of force pushing on it, right? So in the case of no friction, well, how do I solve this? Here, let me just label these for F1 and F2. So the problem is always going to give us some kind of F1, and it's going to ask us to find what kind of force block 1 exerts on block 2. Well, if we consider this whole thing as one system again, they're both going together. They're both going at the same acceleration. So A is constant, just like with the pulleys. A is constant. So this force, this F1 force, is pushing on both of these boxes. All right? So therefore, F1 over M1 plus M2 is going to equal our acceleration because F equals MA, right? And at the same time, this F2 force is just pushing on M2. So F2 over M2 is going to equal to our acceleration. And setting these two things equal, because they're both equal to the acceleration, F2 over M2 equals F1 over M1 plus M2. So F2 is going to equal M2 times F1 over M1 plus M2. All right? So this, again, is what we can do with a problem like this. All right? So the important part here was to consider the entire thing as one system, which really simplifies the problem a lot. Of course, you could have done it the other direction. There's another way you can do this where you consider each box by itself. Right? If we just consider M1, there's this F1 force going against it, right? And then what about F2? Well, according to Newton's third law, M1 is pushing on M2. So M2 is pushing on M1 in the other direction. F2 is actually pushing on M1. So this again is why the third law is so important and always really sneaky as well. Okay, and if we were to do M2, there is just the F2 force. All right, so you could have found it in this way as well. All right, so there are two ways to solve this kind of problem. So let's do this one. This is basically just a copy of what I just did. So you guys should be okay with this one. So basically the critical point in this problem is to know that A is constant. This is the crucial part of this problem. Oops. Give you guys 2 more minutes. Okay, I'm going to go through this problem now. So there are two ways to do this, as I said before. First way is to consider these two blocks as one big mega box of 12 kilograms, right? Because 4 plus 8 equals 12. So if we consider this as one mega box with 10 newtons, the acceleration of the mega box is 10 equals 12 times acceleration, right? And if we consider the acceleration on just the 8 kilogram box, whatever F it is, that's going to equal 8 times the same acceleration. So if we solve for acceleration here, that's just 8 equals 10 over 12, which is something like 8.833, yeah? So if we plug this into here, we're going to have F to equal to 6.667 newtons. All right, so that's the force that that box 1 is exerting on the second box. The other way you could do this, if you were to consider these boxes individually. All right, there's a 10 Newton force pushing on the 4 box, but there's also the equal and opposite reaction force that's pushing back on it. All right, the third law. So the net force on the 4 kilogram box is 10 minus F, and this will equal to 4 times whatever acceleration it is, right? And for the 8 box, I just have an F, right? So the net force on the 8 box is just whatever F it is, right? And this equals 8 times acceleration. So now I have 2 equations and 2 unknowns. So if I plug F equals 8a in here, then 10 minus 8a equals 4a. A again, 12a is 10, and we'll get the same acceleration, and therefore the same force. All right, does everyone get that? So there's another question here, but I'm going to skip that for now. And it's actually a really, really common problem. It's really similar to the other one. So let me go through stacked blocks now, because we're kind of running low on time. This is probably one of the most challenging problems in basically Newton's laws. So a common example of stacked blocks is a 6 kilogram box rests on this frictionless surface here, and a 3 kilogram box is resting on top of it. The coefficient of static friction between the boxes right here is mu s equals 0.3. The force is applied to the bottom box. What must its minimum value such that the top box will start to slide? Well, if we were to visualize this with a calculator and maybe one of these things, right? If I were to push with a small force, then this thing's going to stay on. But if I push with a large enough force, it's going to slip right off of it. All right. So what is preventing this thing from slipping, preventing the top box from slipping off? Well, it's actually the static friction, right? Because if you were to look at a reference frame relative to the bottom box here, let's just pretend this is the 6 kilogram box. We have the 3 kilogram resting on it. If we consider this as a reference frame, then the 3 kilogram box will want to slide backwards, right? But what's resisting that force, pushing it backwards? Well, it's going to be static friction, pushing it forward. So the force involved in keeping this box from slipping off is actually static friction force, right? So it's kind of non-intuitive, but static friction force is actually pushing this box forward in this case. Because otherwise, this box wants to slide off, right? Because this wants to slide off while the calculator moves forward. It wants to, right? But static friction will keep it in place. So as we know, static friction has some kind of maximum value, right? And this is going to give a maximum acceleration that this 3 kilogram box is able to attain, right? So to find this acceleration, I'm going to take my normal force, which is mg, times my mu, 0.3. And this is going to equal to my 3 kilogram box times its acceleration, max. A max. I'm going to label that as A max. All right. So F equals ma here. So A max is actually the maximum capable acceleration, the friction force on the top box is able to push it forward. All right. So these 3's will cancel out. So my A max is actually going to be G 9.8 times 0.3, 2.94 A max. Right? And so if this bottom force is big enough to slide the 6 kilogram box fast enough above A max, then it will overcome the static friction force and the top box will start to slide off. All right, so we want to find the point where F is exactly equal to A max. All right, someone is requesting control of my screen. Can you please stop that? I can't undo that right now. So we want to find the point where this F will accelerate the bottom box at A max. All right. So now let's look at the 6 kilogram box on its own. We have an F pulling on it, and we have no friction between 6 kilogram box and the ground, so we don't need to, we can ignore that at this point. But then if you see here, we have a static friction force propelling the 3 kilogram box forward. So if we look at a close-up of these two surfaces, we have a static friction force pushing the top box forward. And according to Newton's third law, once again, we need to include the static friction force pushing the bottom box backwards. All right. So when I first encountered a problem like this, I completely forgot about Newton's third law. So you cannot forget about it. Once again, it's really important that you remember it. So actually, the friction force that's propelling the 3 kilogram box forward is propelling the 6 kilogram box backwards. All right. And this is, again, right here. This is given by 3g times 0.3. All right. So now my net force on the 6 kilogram box is F minus 0.9 g. All right. As you can see here, this is what it is. All right. So net F equals ma, which is 6 times my A max, right? 2.94. This equals F minus 0.9 g. So now if I solve for F, I just do 6 times 2.94 and add 0.9 times 9.8. F equals 26.46 newtons. All right, so once my force is greater than 26.46 newtons, then the top box will slide. All right, does anyone have any questions with this? This is a really, really challenging kind of problem. So a lot of things are in play here. We have net forces, we have friction, we have Newton's third law. So it's a lot to handle. So it's always important that you draw out these force diagrams and you can see clearly where the forces are applying. So this is the last problem of the day, and this will probably take a while. So since I started class 4 minutes late, maybe I'll give you guys, I'm going to go on with class until maybe 9:04 or something. So I'm going to give you guys maybe 5 minutes to do this one problem. All right. But this is really similar to what I just talked about. So if you find this a little hard, don't worry. This is one of those competition problems I was talking about. And yeah, so if you can't do it, it's totally fine. So as we can see from this problem and many others in the past, little Johnny is in need of some obedience. He's quite a naughty child. So I know this is quite a challenging problem. So as long as you give enough thought into this kind of problem, then that's basically the important part. The important part is to put the thought into it, think through the problem, and if you don't get it, then that's totally fine. The process through solving these difficult problems is what counts. Yeah, so I know it's past 9 o'clock now. If you guys really need to leave, then you can go ahead and do that. But I will go through this example in a few minutes. And since we started a few minutes late, I'm going to go a few minutes over 9 o'clock as well. Okay, so I'm going to go ahead and explain this since this is quite a difficult problem. So if you don't understand the explanation on the first go, I'll always upload the recording of the lesson to YouTube and you can watch it over again. All right, so let's go over this problem. Little Johnny, again, very naughty child, sees a vase on the edge of a table. The table has a mass of 20 kilograms and the vase has a mass of 4 kilograms. If the coefficient of friction between the table and the vase is, 0.2, and the coefficient of friction between the table and the ground is 0.3, what minimum force must he exert so that the vase will fall off and break? So this is just like a stacked blocks problem, right? So we have a big block, table, 20 kilograms, all right? So then we have a 4 kilogram vase on it. Okay, so basically we want to find the minimum force little Johnny has to push the table so that the vase will slip and it will fall off the table and shatter, and meaning his mission would be accomplished. All right, so basically, again, what is preventing the 4 kilogram box from sliding? Well, it's static friction, because if I push my calculator fast enough, this thing is going to start to slide off, right? Because it wants to slide off, kind of, right? So the force opposing this wanting to slide off motion is actually static friction, because relative to the 20 kilogram box, if the 4 kilogram box doesn't slip, then it's not moving, right? Relative to the 20 kilogram box. All right, so it's going to be static friction, kind of static friction that keeps this box and prevents it from falling off and breaking. All right, so my pen has stopped working again. So we have some kind of mu right here. I'll call this mu1, 0.2. All right, so if we look at the 4 kN box right now, the normal force will be 4 times g, right? The normal force. So the maximum static friction force is normal force times mu, 0.2 times 4g. So this will be 0.8 g. So this is the maximum capable frictional force, right? And using this, we can find the maximum capable acceleration that the 4 kN box will handle. So whenever little Johnny pushes the bottom box forward fast enough above this acceleration, then the 4 kN box will start to slip. This equals ma, 0.8 g equals ma. So 4 times the maximum acceleration. I'll label this A max. So A max will be equal to 0.8 times 9.8 divided by 4. A max is 1.96 meters a second squared. Alrighty, so this is the maximum capable acceleration that the 4 kN box is able to go forward at. So if little Johnny is able to accelerate the 20 kN box faster than this, then the 4 kN box will start to fall, right? So now let's look at the forces on the 20 kN box. We have, this time, different from the last time, we have a mu2 between the table and the ground, right? And that's 0.3. All right, so we have a 20 kN box here. So in this case, now we have to look at the normal forces on the 20 kN box that are gonna be in charge of some kind of frictional force between the box and the table, the box and the ground, all right? So how do we find the normal force here? Well, obviously there's an mg going down, which is 20g. Let me label that as 20g. But now we can't forget that there's a 4 kN box on top of the 20 kN box. All right. So the 4 kN box is almost like a calculator on my head. It wants to push me down, right? So adding on to the 20g force, we have another 4g force pushing this box down. And then we have the normal force. So normal force in this case is going to equal to 20g plus 4g, 24g. All right. And so the kinetic friction force between the table and the ground is going to equal to this times the mu, 0.3. So that's just 24 times 9.8 times 0.3, 70.56 newtons. All right, so that is the frictional force between the ground and the table. Well, now we can't forget, again, just like in the last problem, the frictional force pushing the small box forward is also pushing the bottom box back. Newton's third law, once again. All right, so now we have the same frictional force trying to push this back. So what is this frictional force? Well, this is, again, as shown here. It's always important to show your work. And so you can find these values right on your paper. This is 0.2 times, oops, my pen is acting up again, times 4 times g. All right, so what is this force? 9.8 times 4 times 0.2, 7.84. All right, so now we have all the forces we need for the 20 kN box along the x direction. So now the net force, sum of all forces, is going to equal to little Johnny's force minus 70.56 minus 7.84. And this is going to equal to the mass, which is 20, times the maximum acceleration, as shown here, 1.96. All right, so now we just need to solve this for f. And doing that, 1.20 times 1.96 plus 70.56 plus 7.84. Final value for f will be 117.6 6.6 newtons. And this is the answer. Okay, so as you can see, there are a lot of things going on here. And if you didn't quite understand the solution right now, that is totally fine. You can always go over the solution again on the YouTube video I will upload later. And so this is, once again, a competition problem, like a really common problem on competition. So this is quite a difficult problem here. So if this was a little too difficult, don't stress about it, and that's totally fine. All right. So I hope everyone enjoyed class today, and good thing Zoom didn't kick us out. And if you do go to my YouTube channel, please subscribe to me. That really helps the channel a lot. So good night, guys. I'll see you next time. Hope you enjoyed class. Bye.
I'll subscribe.
Thank you. Please subscribe.